Welcome to the Engineering Update. I'm PC Bonetta, editor of ECN. In this week's episode, bladeless wind turbines, a super strong micro robot, and tracking bridge stability. Wind turbines, like all energy sources, come with their fair share of problems. They can be loud, take up a lot of space, and some people, definitely not me, think that they're ugly. Plus, they have a tendency to kill birds. But there's a new design that would solve some of these problems, maybe not the ugly one. A company called Vortex Bladeless utilizes a different aspect of wind power called vortices. Vortices are created when wind moves around a barrier in its path. That movement, which is strong enough to cause bridges to fall, creates a vortex behind the barrier. This new turbine, made of carbon fiber and fiberglass, is designed to take advantage of that vortex in order to create energy. They look a little bit, well, as one of the founders said, a little bit like an asparagus. The motor is at the bottom instead of the top, and the whole design technique means that the turbines don't need giant blades that generally characterize wind farms. The cone shape helps create a perfect vortex to create energy from, plus there's a ring of magnets that keep the cone rotating whether or not the wind is howling. In fact, the company claims the turbine can adapt to any wind speed. In addition to the lack of blades, there are a few other benefits to the design. For one, there aren't any whirling death blades for birds to fall prey to, though the opportunity to nest on the turbine might be a problem. They're also cheaper to manufacture and cheaper to maintain because there are fewer moving parts. Perhaps most importantly, to those who live nearby, the system is completely silent, and they can be placed close together, which limits the footprint necessary for a wind farm. Though the vortex is currently being tested, it will be interesting to see how efficient it really is. Bladeless turbines aren't unheard of, but they generally don't function in this particular way. The team is hoping to debut the Mini, a 4 kilowatt, 41-foot high unit for residential and small-scale farms, and eventually the Grand, which is being designed for more industrial uses.
Micro-robots are taking the robotics kingdom by storm, but tiny new gadgets being developed by Stanford University researchers are headed to the top of the pack. Researchers use the van der Waals force, or the sum of the attractive or repulsive forces between molecules, to build their strength. In other words, it's the same force used by ants to pull heavy loads, which is why these microbots are likely to be the hardest working creatures in their kingdom. The insect-like robots can tow weights up to 46 pounds. That's nearly 2,000 times their own weight. How is this even possible? The robots, also referred to as micro-tugs, use a special directional adhesive deposited onto a series of flexible silicone rubber wedges. When the tips of the wedges make contact with the surface underneath, the robot can move freely without resistance. But when the wedges are pushed down, the microbots stick firmly to the ground. Using actuators, the micro-tugs can quickly switch continuously between the two states to pull its heavy loads. While it's likely we'll see these robots being put to use in factories and construction sites, we'd just like one to drag us over a cup of coffee.
Infrastructure has been an intense topic of debate recently. There are tons of bridges in the US that are beginning to move towards their not-so-stable golden years, and any bridge is susceptible to damage during high winds or crazy weather. So a team from ESA and the University of Nottingham have come up with a way to easily monitor bridge stability in real time. Using sat-nav receivers and ultrasonic wind meters on the Forth Road Bridge in Scotland, the researchers were able to track movements as small as 1 centimeter. However, it was also noted that the bridge can move up to 3.5 meters laterally and 1.83 meters vertically under a wind speed of 41 meters per second. After being transmitted via satellite, the information, which was taken from several key spots on the bridge, was sent to a web-based interface as a part of the project for Global Navigation Satellite System and Earth Observation for Structural Health Monitoring. The study of the bridges is two-part. The researchers must use the real-time data as well as consider what changes in the geography could do to affect bridge stability. For this particular Scottish bridge, it was discovered that there had been no change to the surrounding structure or soil. But that's not always the case. Bridges in China have had notable shifts in stabilizing ground due to groundwater extraction and underwater engineering. However, even without the shifting of the earth around the Forth Road Bridge, the increase in traffic from 30,000 to 40,000 cars daily and 60,000 cars on the weekends means the bridge is undergoing structural stress. This information is extremely useful in deciding when and if to close the bridge, which can have an extreme financial effect, as closing just one lane can mean up to £650,000 in lost revenue. This research allowed the bridge master to use the information to decide when to close the bridge.
That's all for this week's video. Be sure to check us out on Facebook and Twitter and see past episodes at ecnmag.com. I'm Jamie Wisniewski, ECN's newest edition and associate editor, and this has been your Engineering Update.